Hello and welcome. In this particular video, we're going to learn what is called data leakage. In fact, data leakage is one of the critical issues when it comes to building machine learning models. In fact, the data science ecosystem as a whole, data leakage is a big deal. Okay, so we're going to learn what is data leakage and how to deal with data leakage. Okay, so let's get started. First, let's understand what data leakage is. Then we move on to some other concepts that are more important. Okay, so what is data leakage? Now, data leakage actually happens when you train your algorithm on a data set that includes information that will not be available at the time of prediction. All right, so you have data sets that you're using to train your model, and normally what happens is that when you have a data set and you're building machine learning model, you divide the data set into two, that is training data and testing data. Okay, now when the model is actually being built, at the process of building the model, there might be some features that are present at that moment. Okay, and then based on that feature, you build the model. However, in the future, when you use the model in the real world, that data set, that data point or feature might not be available, right? Which our model has already learned when we're during the training time, right? The model has learned from that feature, but the feature is not available during the testing time or during the real world production, right? I will show you an example as we progress. Okay, in simple terms, I mean, if you divide your data into training and then testing, what we aim to do is that we train our model, that is our machine learning model, on the training data, and then after the model has learned from the training data, we test to see if the model has really learned very well. All right, so we use the testing data to test the model. Now what happens is that there are some data preparations and there are some other things that will make your model actually get to know the testing data even before you use it to test. Okay, so just think about it this way. Let's say you are in a classroom, right, and then your teacher gives you sample questions. Okay, you use that as an exercise. You use those questions as a midterm exams, and then in the main exams too, the same questions are coming. Okay, so you already know. You already know the questions. You've learned it. You've used it in your exercises. You've used it in your midterm, and I mean during the final exams, that is during the testing time. You also come to see that okay, it's the same questions that are being present. Of course, you score very well. Right? You score very well in it. So in that case, we say that the question paper leaked. Okay, the question paper leaked because the students have already seen the question paper. So we say that the question paper leaked. In the same way, the data that you're going to use to test is not supposed to be seen by the model. Okay, it's only supposed to be seen when the model has already learned from the training data. Just like you learn from the normal concepts that the teacher will teach you, and then you go and write the exam, right? You are not supposed to see the exam paper before you go and write it. But in the same way, your model is not supposed to see the test data before you use it to test it. All right, so if your model in some way or somehow gets to know the test data, if you use to test the model, it's going to perform very well. However, if you take that model to production, it's going to fail. Okay, it's going to fail. So let's see why this data leakage is actually important and why it's actually a big deal when it comes to the real world scenarios. Okay, so normally what happens is that it can be very deceptive, right? It can be very deceptive because the model has already learned, right, and it is going to overrepresent its generalization error. What do I mean by this? What I mean by this is that normally there's supposed to be an error. You cannot have a model which will make 100% predictions, right? In the real world, it won't work that way. You will not have a model that will make 100% predictions, right? There should be some kind of error. But if your model has learned from both the training and the testing data, it's going to perform very well and maybe very, very minimal error. Okay, but when you take it to the real world where it has not seen any that data point that is coming in new, it has not seen it before, it's going to fail. The same way with the students. If the student has seen the question paper very well, it's going to perform very well. However, if you take the same student to a different, or maybe a national competition where the student has never seen those questions before, the student is going to fail, right? Meanwhile, the student is performing very well during the classroom or the class exams, right? Because the student has not seen the national exam before. However, the student was always seeing the final exams of the classroom. Okay. In the same way, the model will do. Okay, the model will fail because it was only performing well because it has seen the data before. All right, so that's actually one of the problems associated with this data leakage. Okay, the next one that you can think of is that let's say financial investment, right? So we have investors that normally make investment in stocks, right? So if you build a model to predict certain stocks that investors are supposed to invest in, and the model is not actually predicting very well, it has just learned from the past data that you have fed it to it, and overlearned it and memorized it, right? And it's performing very well. Then you're using that model to make prediction that, okay, if we invest in stock A, we will actually get a huge profit within the next 2 or 3 weeks or something like that. And then investors put their money in. It's actually going to result in a huge cost, right? A huge financial cost, which is quite dangerous, right? So that is one of the another big problem with this. In fact, the most critical problem with this data leakage is related to the healthcare sector, right? So if patients are if there's a certain kind of outbreak of a disease, and your model is predicting that in the past people got this kind of a disease. So if you take, say, the coronavirus, for instance, and your model is predicting that during the Ebola time, doctors used, say, paracetamol to cure the patients. So if there's an outbreak of coronavirus, we can also use paracetamol to actually cure the coronavirus. Then you are making a mistake, right? It's just because your model has learned very well from the past data. Okay, it has memorized it. It has memorized it, the past data, and it's making wrong predictions of the future. Okay, so this is very critical, and it's going to end up killing a lot of people, right? Your model is going to end up killing a lot of people. So, critical care needs to be taken before actually deploying such kind of models. Okay, in fact, if you take, say, e-commerce sector, right, and then you are building a model to predict customer behavior, right, whether the customer will purchase some items or which items are customers purchasing frequently, and then your model is actually making the wrong predictions based on the data that it has already seen, and it's making a good prediction that, okay, if we put let's say it's getting to winter, so let's put more of black coffee, right, on our e-commerce website, because during winter most people are going to take coffee, and then it comes to the real world, and most people are not taking the black coffee. Maybe they take coffee, but not that particular brand that you are putting on your e-commerce site. You're going to end up incurring a lot of huge cost. Okay, so your model can make such kind of deadly mistakes, right, when it has overrepresented its generalization error. All right, so data leakage is quite a critical issue when it comes to the real world machine learning or data science in general, okay, when building models. All right. So at this point, you might be thinking, how do I even know if I'm having data leakage, right? So to be honest, there are no fast and easier way to detect that, all right? But however, if you build a model, if you build a machine learning model, and your model is actually unrealistically having higher performance, right, on the test set, unrealistically having higher performance on the test set, the test set has not been seen by a model. So obviously we normally we expect it to have a little bit of a lower performance as compared to the training data which it has already seen, right? So it's supposed to do very well on the training set, as compared to the test set. However, if you build a model and you see that your model is doing very, very, very well on the test set, that model should be suspicious, right? You should start suspecting that model, that there's might be something wrong. I mean, data leakage is one of them, but there might be other things that you did wrong when you are building the model. Okay, all right. So you have to check if your model is doing something like 99.99% on the testing set. It's actually suspicious, and you have to actually go back and then check the process that you took when building the model. All right, and you also might be thinking, I mean, what causes this? What are some of the possible causes of this data leakage? All right, so these are some of the possible causes of data leakage. There might be duplicate values in your data set. There are something we call leaky predictors, which we will see in a jiffy, and also the process that you took when building the machine learning model. Right, so all these are some of the things that can cause data leakage. There are quite a lot of them, but these are the prominent ones that can cause data leakage. All right, so let's see. When I say duplicate values, right, what do I mean by that? Now, if you're building a machine learning model, it's quite possible. So the example that I told you earlier on about students having seen the questions before going to write. So let's say you actually give the students the same exam question in their class exercise. They have already done that. You discuss the solution with them. You brought the same exercise in their midterm exams. You discuss the solution with them. Now they are getting more familiar with this exam paper that you're giving them. Now they know the A's and B's of the exams. They know the ins and outs. They know the solution already, right? Now, if you're going to use the same question paper to test them at the end of the paper, they will actually score very well, right? Because you've given them the same thing over and over again, right? You've duplicated the same question paper over and over again, right? So they will do well, right? So they have duplicate information in their memory. They know it's the same information you're continuously giving to them over and over again. All right. If you take real world example like customer reviews, right? So let's say you want to build a sentiment analysis model, right, on customer review on, say, Amazon products, right? So people buy products from Amazon website, they write reviews. So you want to know the sentiment, whether the person liked the product or not, right? Whether the person is feeling good about the product or feeling bad about the products they bought. So in that case, you want to scrap data from, say, Amazon website, the reviews. You want to scrap them and then analyze them and see the sentiment in it. Okay, in that case, it's possible you're going to get duplicate values or duplicate data points in there, right? Because some customers will write reviews, same reviews over and over again. Maybe the product owner will motivate them to write more reviews so that it will be like a social proof, and others will also go and then buy the product. So the same customer will write the same reviews for the same product over and over again. Okay, and it's actually going to be duplicate. Or maybe the customer likes the products so much that the customer keeps writing the same reviews, with the same sentiment, whether the same positive sentiment, or the customer doesn't like the product, so the customer keeps on writing the same bad or negative reviews over and over again, right? So it's just the same information the customer is writing, but it's writing at different times. So in that case, it's going to be a duplicate information or duplicate data that you have, right? And your model is just going to learn from that and make get a good accuracy. But meanwhile, it's actually basing on the duplicate values that you're going to to it. Okay, and you're going to use same data sets. You're going to divide it into two, into training and testing, and use some to test the model. So obviously your model will do well, right? But if you take it to the real world production where you have different reviews with different sentiments, it's actually going to fail. Okay, so you have to be cautious when you have duplicate values in your data set. All right. Now, there's another cause of data leakage which we refer to as leaky predictors, right? So let's see what these leaky predictors are. And in fact, this happens when your data points are you have data points which some of the predictors are highly correlated with a target variable, right? So when you're going to make a prediction, right, especially when you're dealing with supervised machine learning problems, right, so you want to use certain data points to predict some targets, right? Maybe you want to predict the price of a product, right? You want to base on certain things and then predict the price of the product, or you want to know whether a customer will purchase a product or not. Okay, so you want to base on certain customer behavior data that you have, right? You want to base on that and then predict whether a customer will purchase an item or not. So in that case, if you have some of the variables that are highly correlated with whether a customer will purchase or not, then you actually going to end up building a model which will memorize a certain patterns and then make a higher predictions. Meanwhile, if you take that variable to the production, if you take that model to production, it's going to fail, right? Because it's possible that the variable which is helping you to make that good prediction might not be available by the time that you're making the final prediction, right? So leaky predictors actually happens when you have data points, right? When you have data points that will not be available at the time you are making the prediction, right? And it normally happens when you're dealing with data where time is important, right? Like time series data. Okay, so let me actually show you an example so that you get to understand what these leaky predictors are. Okay. So what I'm going to do is that I'm going to create a data set, right? Just a dummy data set, and I'm going to see whether a customer will purchase a product or not. So what I'm going to do is that I'm going to create a dictionary, right? So I'm going to have keys as a dictionary of products, whether a customer purchases some products or not. So I'm going to have the keys of the dictionary to be purchased, right? So when you're creating a dictionary, you bring the curly brackets, right, and then the key, right? So it's going to have a key and then the value, right? Key and then the value over here. So the keys that I have over here are the pages, right? The pages of the product, whether the person purchases or not. So it's going to be yes or no. And then the quantity, right? The quantity of the product, and the quantity is this one, which is going to be the value. So someone bought 2, someone bought 5, someone bought 17, 10, 0, 3, 7, right? And then the products, right? The product that they bought, and I'm going to show you some other keys in there. So let me actually do that. And then over here, what I'm doing is that I'm going to convert it into a pandas data frame so that it will be in a table format instead of the dictionary, right? It will be in a table format so that we can actually work with very well. So let me show you what is inside that. Let me show you, let me get rid of this, in fact. Okay, so let me show you what is inside that. So this is what we have, right? What is inside here is that, so I have pages, right? So it's just dictionary that I created, and I converted the dictionary into a pandas data frame. Okay, so I have pages, whether the person pages or not. So the pages is the heading over here, and then the items that I put over here, which is yes, yes, no, no, no. Yes, no, yes, no, no, yes, yes. Okay, so this what we have, and then the quantity that we have, right? So the quantity and the quantities that we have, purchase and discount. Okay, so I've converted everything to a table format just using the pandas data frame over here. Okay, and then pass in my data. All right, so what we're going to see over here is that let's examine this table carefully and then see something over here. So this one is actually relating to a particular customer, so we want to see if the customer will buy an item in the future or not, right? So what I'm going to do is that I'm going to convert this the data that we have here. So we have yes, no, yes, no, yes, no. I'm going to just convert this data into 1 and zeros, because if you're going to build a machine learning model over here, you cannot use these characters or strings or letters to build a machine learning model. You need to convert them to either zeros and ones, or in integers. Okay, so that's what I'm going to do. I'm going to use a label encoder, right? Don't worry about this label encoder. There's a whole session on that where I would we will learn about label encoder, get dummies, and other encoding functions in there, right? So don't worry about that. I'm using it to convert everything to numbers, right? So now you see the new table that we have, right? Earlier on we were having some yes and no's. So if it is yes, it's 1. If it's no, it's going to be represented as 0, right? The same way, if you see the pages, the product is going to start from, say 0 starts from, let me see which one was giving 0 here. 1 2 3. So if I come here, 1 2 3. So biscuits, it started from biscuit 0, and then so it's actually doing it alphabetical order. So B, right? So it's look at B and then give that product as 0. Then it go to C, which is chocolate. It will give it as 1, and then coffee will be 2. Like that. Okay, so maybe biscuits will be 0 and bread will be 1, right? Because this is all BB, so bread will be 1. So it will check the next item, I and then R, right? Which one comes first when it comes to alphabetical order, and then gives it the tags, right? So that's why it's 0 and then 1, right? So bread will be 1. So it's just going to tag them that way. All right, so one thing that you can actually use to determine if you have a leaky predictor is that whether there's a certain feature which is highly correlated with the target feature, right? So in this case, we can check the correlation between these features, right? Correlation between purchase and quantity, correlation between purchase and product, correlation between purchase and discount, and see if there's a very high correlation between one of the between these two variables, like for instance purchase and quantity. Then you know that quantity here, which is actually a leaky predictor, right? Or maybe there's a high correlation between purchase and discount, then you can see that discount is a leaky predictor. Okay, so if we check the correlation, use the core, right? So in Python we have this core function which stands for correlation, right? So we can use that one to check for correlation. Okay, so in that case, if we do that, you can see that over here, let's actually examine this correlation output matrix that we have over here. If we check, let me bring this pen. If you check the diagonals here, right, it's always going to be 1, right? So this is actually going to be 1. That is not our concern here. We are not interested in the diagonal, so we ignore that part. And in fact, this part, right, the top part here, right here, and then here, right, and here, right, if we pick it this way, all the numbers here are the same as the numbers here. So you can take either half of that, right? You can just take, right, like that. Okay, so you can see that the numbers down here are the same as the numbers up here. Okay, so you can make inferences from either half of that. Okay, either half of that. Okay, so if we check the correlation between, say, quantity, right, quantity and purchase, right, let's check the correlation between quantity and purchase. We can see that it's here, right? It's this value, right, which is negative 0.3, right? So that's very low. It's very low, negatively correlated, right? If we check between, say, products, right, between products and then purchase, right? Product and purchase is this one, which is 0.4. It's still low. It's very low. However, if you check discount and purchase, right? You check discount and purchase, now you can see that 0.7, which is high, right? This is very high. So discount is highly correlated with purchase, meaning that as discount is yes or 1, it's likely purchase will also be 1. Right, if discount is 0, it's likely purchase will be 0. Okay, so your model is actually going to learn from that deceptive pattern, and it's going to perform very well. It's going to get a very high accuracy. Meanwhile, if you take it to production, it's possible that this discount feature that your model has learned from will not be available. Right, and that's the problem that you're going to face. That's the problem, why your model will fail in production. Okay, so you need to actually take care of that when you have such leaky predictors. Okay, so not only this, maybe sometimes you also want to scale your data, right? So or standardize the data. So standardization is also one of them, right? So in standardization, what we do is that we calculate the mean of the entire data set, the standard deviation of the entire data set, right? And then we subtract the mean from each of the data points and divide it by the standard deviation. So that's actually going to give us our standardized data. Okay, when we do that, right, each of the standardized data that we have here has tested each of the data points that we have in our entire data set, right? Because we calculated the mean and the standard deviation from the entire data set. So whatever results that we're going to get later on has tested each of the other, right? They all have a test of each of the other. So even if you divide it into training and testing later on, it's still just the same data set that you are going to use to test it, right? So it's just like you've already given the question papers to the students, and then you're saying that I'm going to reprint it on a different sheet and bring it to you, but it's just the same questions on a different sheet. Okay, they already know the questions, they already know the answers, they are going to perform very well. All right, so that's normally what happens when we do normalization and standardization. Okay, so now let's see a different approach of how we're supposed to approach this instead of going the normal way that we normally do, right? So what we actually going to do is that in order to avoid this data leakage, what we can do is that we will first split the data, right? Instead of normalizing or standardizing or doing the missing data imputations and all those things, right? There are a lot of pre-processing activities that land us into data leakage. Instead of doing that first, what we can do is that we can first split the data, right? We can first split the data into training and testing, right? And then this testing data, we hide it, right, from the model. We don't use it for anything unless we are testing the model that we're going to touch it, right? We don't touch it. What we do is that whether we are going to deal with missing values or duplicate values or standardization or normalization, we do everything on this training data, right? This one, we don't do anything to it, right? This one should be safe. We don't do anything to it. We only use it when we are testing the model. Okay, so when we split our data into training and testing, then we perform the data preparation, right? We perform the data preparation. So all this data preparation are going to be performed on the training data, not the testing data. We don't do anything to the testing data. Okay, if you want to do anything to the testing data, you do it separately, but you don't do them together, right? You don't do them together. Okay, you don't do them together. Doing them together is a wrong way to do it, right? If there's anything, some missing values or something you want to deal with it, you do with it separately in the testing data, but you don't deal with it together with the training data. Okay, then after that is done, then you can fit your model and then evaluate the model. So when you're doing the evaluation, you evaluate it on the testing data that you have hidden from the model right from the beginning. Okay, so that's that's the way that you're supposed to do it, instead of first preparing the data before splitting it. Okay, so if you prepare the data before splitting it, there's no use again. All right. The next one that we're going to talk about is pre-processing activities. And in fact, this is actually the most and easier way to land into data leakage, right? This your pre-processing activities. Okay, so let's see what goes wrong normally in this kind of activity. So let me actually open this. Now, when we talk about the pre-processing activities, when you're preparing your data to build a machine learning model, what normally happens is that there are certain steps that you follow before building the model. Okay, before building the model. So these are what I mean by pre-processing. You need to prepare your data before you build the model. You cannot just build the model just like that. You need to do some things. There might be some missing values in there. There might be some data points that you need to drop, or some duplicate values you need to delete, and some other things that you want to do, some outliers you need to deal with, which we're going to see them in this course, right? So there are several steps that you want to take. However, the way you organize your steps is actually having a huge impact on the model that you're going to build. Okay, the steps that you take is going to have a huge impact on the model that you're going to build. All right, so if we pick the approach that we normally use, right, that is the normal approach that we use. We prepare our data, then we split the data into training and then testing, and then we build the model on the training and evaluate it on the testing. Normally, that's what we do. Okay, we actually prepare the data, we split the data into training and testing, and then we build a model, right? We build it on the training data, and then test it on the testing set. This is normally what we do, right? And I mean, while this is most popular in many of the cases, this actually leads out to what is called the data leakage, right? Mostly it leads out to what is called data leakage. All right, so let's see what goes on wrong in there. Now, when you're preparing the data, right, let's say you want to normalize your data, right? If you want to normalize the data, what normally happens is that, right, if you want to normalize the data, you want to maybe bring your data into a range of, say, 0 to 1, right? A range of, say, 0 to 1. You want to have a range of 0 to 1, right? So some data points might be huge, some data points might be less, right? And if you're using distance-based models such as support vector machine, you're going to have a problem. So you want to make sure that your data is, all the data points are within a certain range. Okay, in that case, you want to normalize the data. There's some formulas that we use. For instance, we have we calculate the mean, right, the minimum value of the entire data set, and then we also calculate the maximum value of the entire data set, and then we subtract the minimum value of the entire data set from each of the data points, right? And we also subtract the minimum value from the maximum value of each of the data points, and that is actually going to give us, right, our normalized data. Okay, so we subtract the minimum value from each of the data points, and we also subtract the minimum value from the maximum of each of the data points, and that is actually going to give us our normalized data point. Okay, so this is one of the things that we do. And what happens is that we have already calculated the minimum of the entire data set, and we have also calculated the maximum of the entire data set. So somehow this normalized data, right, which is our X, which we are going to use to build the model, knows something about each of the data points in the data set, right? So if you first normalize your data before splitting it into training and testing, then each of the data points will have a taste of each of them, right, of each other. Okay, they will all have a taste of each other. All right, now let's see some examples of this, right? Let's see some examples of this. So normally we are going to use the approach 1, then we use the approach 2 also. Okay, so let's see the approach 1. So the approach 1 here is prepare the data, right? That is, you first prepare the data, then you split it, and then you build the model, right? So let's do that. The preparation that we're going to do here is we're going to make sure that our data is actually scaled within a range of 0 to 1, right? So let's say that's what we want to do. We want to make sure that our data points are between 0 and 1, right? We don't want our data points to have a different scale. So we're going to use what is called a min max scalar, right? Min max scalar, we talk about it in the following cells, right? What we are trying to say is that if you pick a data set like this, right, you can see that we have weight, length 1, length 2, length 3, height, and then width, right? If you check the numbers that we have in here, right, you can see that we have some 55, 60, 80, 120, 140, 170, 300. If you check this one, we have 13, 14, 16, all the way. If you go to maybe the width, you see that we have 2.3, 2.3, 2.6, 2.9, 3.2, something like that. And then here we have, say, 6 point something, 9 point, 10.3, and so on and so forth. Okay, if you see the values, you can see that some values are very low, some values are very high, right? They are in different scales, right? So this one will be maybe on a scale of 0 to, say, 300 or 0 to 500, right? But if we take the width will be on a scale of, say, 0 to 5. It's a very small scale, right? But if you take the scale of the weight will be on a scale of 0 to, say, 300 or 500. So that would be a huge scale, right? We don't want, to have different scale like that. If you're building a model and using distance-based models such as support vector machine, you're going to have a problem, right? You're going to have a problem because if what is going to happen is that it's actually going to use a distance to measure this. So the distance between, say, if you take the distance between, say, 300 and 273 is higher, very high, and as compared to the distance between, say, 2.3 and then 2.3 over here, right, which is going to be very low. All right, if you take the distance between 55 and 60, right, it's going to be higher, very high. And if you take the distance between 6.8 and 6.5, is actually going to be very low. All right, so what is going to happen is that your model using distance based is going to ignore this part, right? It's going to ignore the distance between here. It's not going to matter most, but it's going to give more emphasis on the distance where on the feature where the distance is quite high. Okay, we don't want to end up having that kind of assumptions. Okay, so we want to scale all of them between 0 and then 1, right, so that they will all have the same weightage, the same we can measure them on the same scale. Okay, so we can use min max scalar to actually achieve that. Okay, so if you see this one here, we have 5.1, 4.9, 3.2, 3.1, 1.4, 0.2. so it's not that some values are very high, some values are very low, right? We don't want that case. We want to have a uniform uniform scale like this. Okay, so let's see how we do this, right? We're going to use the min max scalar to do that. What I'm going to do over here is that I'm going to just generate some synthetic data here, a dummy data over here. I'm going to use this make classification, right? I'm going to use this make classification function to actually generate 1,000 records, right, with 10 features, right? 1,000 records with 10 features. So that's what I'm going to do. And make classification is actually let me do this. Make classification is actually present in sklearn dataset, right? So sklearn dataset, we have what is called make classification in there, right? So I'm going to import that. So from sklearn.dataset, right? From sklearn.dataset, I'm going to import make classification. All right. Then what I'm going to do is that I'm going to actually generate X and Y datasets. So if I use the make classification here, I'm going to generate 1,000, right? 1,000 data points, right, with 10 features, right, with 10 features over here, and then I will actually divide them accordingly to X and Y. Okay, so if you check the shape of X and Y over here, if you check the shape of X, right, and then the shape of Y, you see that the shape of X is 1,000 with 10 features, and then we also have this Y to be 1,000, right? Because this is actually not having any, it's a target column, it's just one series, right? So it's not having multiple features in there. Okay, so over here you can see that we have the data points being generated using the make classification, right? Make classification function over here. Okay, so now that we have some dummy data being generated for us, what I'm going to do is that I'm going to use this min max scalar, right? I'm going to use this min max scalar to actually scale this data, right? So that I will have a uniform scale like this one, but not like this one. Okay, so I'm going to do that. So I'm going to I'm going to initialize it over here, right? I'm going to initialize it over here. So I have min max scalar, then I initialize it over here. So I'm going to initialize it into a variable called scalar, right? You can just name it anything. So over here it could be maybe min max. You can just write into min max anything, but I just name it as scalar, right? You can just name it anything that you want. Then what I'm going to do is that after I initialize it, I'm going to use that scalar to fit and then transform the data, right? I'm going to transform this X that I have, right? So if the X looks like this, I want to transform it, right? If the X looks like this, I want to transform it to this, right? I want it to look like this. Okay, so that's basically what I'm going to do down here. All right, so I do fit transform, right? Then the next thing that I'm going to do is that I'm going to now split it. Now you see the process that I'm talking about. Okay, we first prepare the data by normalizing it, right, to have a uniform scale of 0 to 1. Okay, and then now we are going to split it, right? We're going to split it into training and then testing. All right, so let's see how that is done. I'm going to use this train test split, right? I'm going to use this train test split to actually split the data. Okay, so train test split is actually present in the sklearn model selection, right? So I'm saying that from sklearn.model selection, I'm going to import this train test split, right? Then after I import it, I use the train test split over here. Then I pass in the data that I created, right? The X and then the Y data that I created, right? Don't forget that this X that I'm using here has already been normalized, right? Over here, right? I use the fit transform to do that, right? I mean the min max scalar, then I fit transform that. Okay, then I'm using a test size of 0.2, meaning that I'm going to use 20% of this data points to for testing. Then I'm going to use 80% for training. Okay, that's what I'm actually doing here. Then I'm going to use random state equals 50. I mean this thing is going to be done randomly, right? It's going to select data points randomly. So I'm going to use random state equals 50 so that if I run this code again, I'll still get the same random numbers being generated. Otherwise, if I run this cell again, I'm going to have different random numbers associated with different points, right? So if you see over here, I have X, right, and then I have Y here. The part of the X that is going to be used for training is going to be stored in X train over here. Okay, the part of the X that is going to be used for testing is going to be stored in S test over here. Okay, and the part of the Y that is going to be used for training is going to be stored in this, right, Y train over here, and the part of the Y that is going to be used for testing is going to be stored in this Y test over here. And this process is going to be done randomly, right? It's going to be done randomly. So different values of X are going to be associated with this, randomly associated with X train and S test, right? The same way the values of Y are randomly going to be associated with Y train and Y test, right? In order to get the same random numbers, if I run it for the first time and it selects these numbers randomly, I want the same numbers to be selected over and over again to the same S train and S test, right? So I give random state equals 50. You can just change this number. This number doesn't matter much, right? You can change it, but it's still, once you specify that random state equals something, you're still going to get the same random numbers over and over again. Okay, so that part is done. The next thing is that I'm going to use logistic regression, right? We're going to build a logistic regression model, right? And this is actually present in sklearn linear model. So I'm saying that from sklearn, right? From sklearn.linear model, import a logistic regression. Okay, so once I get the logistic regression, what I do is that I initialize it over here. Okay, I initialize it over here. Then I initialize it into a variable called model. All right, so this model is just a variable name. You can name it anything that you want, but since we are building a model, I just want the name to be more sensible, right? So this is actually a model, and I'm going to use it over here. So I do model.fit, right? So model.fit is nothing but just the model learn, right? So this is where the model actually learns. So you can associate fit to learn, right? So fit means learn. So the model is going to learn from what? It's going to learn from the training, the training data, right? That's the S train and then the Y train. Okay, it's going to learn from that. So over here we have our S train and then Y train. We split our data into training and testing. So you see that we have training and then testing data points, right? So these are the testing, these are the training data points. Okay, so it's going to learn from the training data points. So this is where we use 80%, right? 80% of our data for training, and then we use 20% for testing. Okay, so when we do that, right, our model has learned from the training data points over here. Okay, so that's basically what we want to do. So these are the steps that we have so far. Let's go a little bit up over here. So we prepare our data using the min max scaler to scale our data, and then we split our data into training and testing, right? And then we build our model. So now let's go and then evaluate the model, right? Let's see how we do that part. Okay, so for that, for the evaluation part, what I'm going to do is that we actually going to use accuracy score to check the accuracy score that we have when how accurate our model is able to learn from the data that we fed to it, from the training data that we fed to it, and how accurate it's going to help us in the future predictions. Okay, so accuracy score is present in matrix, right, which is part of sklearn. Okay, so I'm saying that from sklearn.matrix import accuracy score for me. Okay, now after that, what I'm going to do is that I'm going to make some predictions. So this is the model, right? The model that we built earlier on, right? I'm going to use model.predict, right? Now what I'm going to do is that I'm going to make prediction on the training data set and also prediction on the testing data set. Okay, so I'm going to do it too. That's one on the training. Okay, this thing is not writing well, but yeah, fine. So I'm going to do one on the training and also one on the testing. Okay, so as you can see here, one on the training data and the one on the testing data. Okay, so I'm going to do two different predictions. All right, so let's see how it's going to predict. So this S-train is a data that it has already learned from, right? This S-train is a data that our model has already learned from, and this S-test is a data that our model has not learned from, right? So ideally, it's supposed to be a data that our model has not seen before, because if you take this model, right, you take this model to production, you're going to feed it with the different data from the real world where the model has never seen it before. Okay, so this test is supposed to represent that kind of data. Okay, right, but when we're scaling the data, we have already used part of this data to scale it, to scale the the S data, where we divided it into training and testing already, right? So somehow this model knows something about this, right? Somehow this model knows something about this, but ideally it's supposed to not know anything about this, right? But somehow you know something about it. So let's see what happens over here. All right, so I do model.predict, right, and then I predict it on the training. And then I use the accuracy score, right? I use the accuracy score to check the Y predict. That is the data that we have before, at hand. That is the Y train, and also the prediction that we are doing. So it's more like we have something like this, right? So we already know something. This is what we know, right? And this is what we are predicting. So we want to see if what we are predicting, so if here is 1, if we predict 1, we want to see that is it the same as what we know? Is it the same as the one that we know, right? So if we have 0 here, we want to be able to predict 0. If we have 2 here, we want to be able to predict 2 here, right? Or if here is yes, right? If here is yes, we want to predict yes. Okay, we want to predict yes. If here is no, right, we want to be able to predict no. Okay, so that's what we are doing here. We are comparing the two to see how accurate that we are doing. So that's what we are using accuracy score over here. And then let me get rid of this. After that, we actually just convert everything to a percentage. Okay, then we do the same thing for the test, right? So we have Y test and then Y predict over here. So let's see the result, right? Let's see the result over here. So if I show you the output over here, so the accuracy of the training set, right? So we have 88. Right, so in the training set, that is the model, the data that it has already learned, right? The model has already learned from the training, right? So if you check the accuracy, how well it's able to predict what it has already learned, right? So it's more like we are checking how well a student is going to perform on the same exams the student has seen before. Okay, so that one is giving us 88%. And if we check it on the data that our model is not supposed to have seen it before, in that case it's doing 91%, which is the S test, right? It's actually giving us 91%. Now we will compare these two, right? It's actually, if you see it like this, it's actually doing well, because 91% is a good accuracy for us, right? If your model is doing 90 and above on the testing data, it's actually doing good, right? It's actually doing good. Now let's see the right way of doing this and then compare the two. Okay, So first, we've dealt with this, where we prepare our data, split it into test and set, test set and training set, and then build the model, right? So now we're going to see the second approach, which is the right way to do it, right? So the second approach is to first split the data before you scale it, right? Not scale before you split before you scale, okay? So we generate the dummy data again over here, then we split it, right? So right from the beginning, we split our data into training, right? That's S train, S test, Y train, Y test, okay? Then we do the scaling. So this part we are doing the scaling. So we have split the data, then we scale the data, then we build the model. So it's just the same code, but the format has changed, right? Instead of this part first, that is min max scalar first, like we did earlier on, right? So at first, if you remember, we did the min max scalar first. We scaled the data, right? We scaled before splitting. Now what we are doing is that we are splitting before scaling, okay? Then the rest of the process is the same thing, okay? Now if we check the accuracy over here, this one, if you check the accuracy over here, now you can see the difference. We have 88% for the training, 48 for the testing. You see, right? It's actually doing terrible, right? So although our model is not doing well, it was actually overfitting, but this one, the process that we did first, could not actually reveal that to us. It was still telling us that our model is very fine, it's doing very well, right? It's actually deceptive. It's telling us that, oh, when we take it to production, it will perform very well, to do very, very well, like 91%, right? Then we will be happy. But actually, that's not the reality, right? Now the reality has been revealed over here, right? See that it's going to be very, very terrible. 48 is the worst you can have. I mean, it's just bad. You can't take this thing to anywhere. You can't take it to production, okay? You can't do this. I mean, no company will allow you to deploy this model, okay? But if you do it this way, it's actually deceptive. You will think that you have built a perfect model, but that's not the case. That's very bad. So the conclusion here is that check the step that you take to build the model, okay? Check the step that you take to build the model. The other thing that you can also do is that to use cross validation, right? To use cross validation. So what it's going to do is that it's going to divide your data set randomly into training and then testing, okay? So over here you can see that let's say this is all the data points that we have. So you're going to do it iteratively 5 times, right? So for the first time, it's going to hide some part of your data set for testing, and it's going to train your data on the other part, right? When you do the second iteration, it's going to hide another part of the data set for testing, and then perform all the other operations on the other data set that is for training, okay? And then it will do another iteration, right? So for example, iteration 3, then it will hide another part, right? A different part for testing. So you're going to do this iteratively several times, and then at the end of the day, it will calculate the mean of the, this one, if you do it for the first time, you have an accuracy. If you do it for the second time, it will have an accuracy. If you do it for the third time, it's going to have an accuracy unto the number of times that you specify, right? So it will find the mean of the accuracy, right? The average accuracy, and then give you that accuracy, okay? So that's actually another safe way to do it, right? Using the cross validation. It's actually a safe way to actually do it, okay? So this one will actually be done automatically for you, hiding some of the data set for testing, right? And then using some for training. However, you can also mess up with this, right? If you don't take care, you can also mess up with this. So let's see the right way to do this cross validation as well, okay? So first, let's see the wrong way to do it, then we see the right way to do it, okay? So I'm going to just generate the same dummy data points that we did earlier on, okay? And then some mistakes that people do at first is after they have their data set, they first scale it, okay? As you can see over here, they first scale it or perform the data preparation before they use the cross validation, which is wrong, right? You're not supposed to do that. I'll show you in the next, in the approach to the right way, okay? So if you do that, if you first scale the data before performing the cross validation, so over here I'm using cross val score, which I'm going to use later on. So cross val score is actually present in model selection, which is part of sklearn. Okay, so I'm going to say that from sklearn.model selection import cross val score for me, and then I'm also going to use this repeated stratified k-fold, which is what is going to actually divide our data set into in several folds or several groups, and then perform this testing and training for us. Okay, and this is actually also present in model selection, which is part of sklearn. Okay, so I'm going to use from sklearn.model selection import repeated stratified k-fold. Okay, now after that is done, what I'm going to do is that I'm going to just initialize it over here. So I'm going to initialize this repeated stratified k-fold that we imported, right? I'm going to initializing it into a variable called CV, just for cross validation, right? And then I'm going to split this one 10 times into 10 parts, right? And I'm going to do this repetition 5 times. Okay, setting random state to be 50, so that the same random numbers will be generated for me each time that I run the code. Okay, so after that, what I'm going to do is that I'm going to check the score, right, using the cross val score that we imported earlier on, which is this, right? I'm going to use that. Then I put my model that I built earlier on, and the CV over here, which is what I have initialized, right? And then I have my X and then Y. Okay, and then the scoring that I want is accuracy, right? I want the accuracy. And then the CV that I built, I created over here, right, which is this CV. I just bring it here, which is the cross validation. Okay, now when that is done, when you set up it like this, right? More of this in the machine learning class. We see more of this in the machine learning class, where we go into details with this one, right? But this one to show you the process, right? To show you how you're supposed to do it. All right. So after this part is done, if we check the performance of that, as I said, it's going to do this several times, and each time that it does it, it's going to have an accuracy, right? So we want the average accuracy, right? The mean of the accuracies. So what we're going to do is that we're going to actually use NumPy mean, right, to find the mean of the scores, right? Remember that when we do it, we get all the scores. We get all the scores in this variable called scores over here. So we find the mean of that, and then we actually multiply it by 100, so that it will be in the form of a percentage for us. Okay, so if we do that, we see that we have around 88.76%. all right, so what we have done here is that we have first scaled the data before using the cross validation, which is the wrong way to do it, right? You are not supposed to scale the data before. What you can do is that you can use a pipeline. Okay, you can use a pipeline to actually do that without first scaling the data, right? If you want to perform any scaling, put everything in a pipeline, right? So sklearn is having what is called pipeline. Okay, so pipeline is present in sklearn. So I'm going to do from sklearn.pipeline import pipeline for me. Okay, so that is what you can do. Then what you can do is that here you generate your data. So whatever data, if it's in a CSV format or whatever format that it is, you just read your data here, and then you create a number of steps, right? You create a number of steps that your cross validation is going to follow, right? So after you create the steps, right, more of this in the machine learning class, but just to give you how things are supposed to be done. Okay, so after you create your steps, what you're going to do over here in the pipeline is that you're going to put the steps right in the pipeline. So pipeline is just like a template that is supposed to follow, right? That your model is supposed to follow to build the model, right? Then your CV, right, which is the same thing that we did earlier on, right, is going to come over here, right? It's going to come over here. You use the repeated stratified k-fold over here, and then you use your score, which is the cross validation, and then you put your pipeline in there, your X and then the Y. You check the scoring to be accuracy, right? And then the performance, you find the mean of that, right? The mean of the scores that you have. Okay, So if you do that, right, if you do it in the right way, you see that this one we have 85.43, right? Although this one is giving you 88, but this 88 is going to fail in production, right? Because you've already scaled the data over here before using it. So somehow the data that is going to use for testing, right, if you split the data into test and training, right, this test is part of this training, right, as well as this training is also part of this testing. So nothing has happened even if you split it. However, if you don't split, I mean, if you don't scale it earlier before splitting it, it's actually going to give you, I mean, a more generalized model, right, which you can use in production, which will fit into the real world data that might come in. Okay, so that's how you're supposed to do it. Check the steps that you use, right? So the right step and then the wrong step. You have to be careful which one that you're using, right? The right approach and then the wrong approach. Okay, so approach 1 and then approach 2, right? Approach 1 is where you prepare your data before you split it and then you build the model, right? The approach 2, which is the right way, is to first split your data and then perform the data preparation, fit the model, and then evaluate it. All right, so I hope now you have a better idea of data leakage and how you're supposed to go about avoiding data leakage. All right, so see you in the next video. Bye bye.